We consider an economic model here, which again is running under some constraint. Suppose that we have a quantity of a product Q, and the amount we can produce depends on, unsurprisingly, the number of workers, and also the number or the amount of capital investment. And there's a classic family of functions called the Cobb-Douglas functions that are typically used or commonly used for this kind of model. So the quantity produced is going to be 6 times the amount invested in workers, or number of workers, to the power 3/4, times the amount invested in capital, K for German Kapital, to the power of 1/4. Now, these things are not equal in cost either. So it costs $10 per worker, say per hour, and capital costs are $20 per unit. And we have a budget of $3,200. So what can we do with that kind of information? Well, we obviously want to optimize the production given the amount we're spending on our workers and capital, and we'd like to find the optimum distribution of capital and workers. So how do we go about that? Well, our budget defines the constraint here. That's what's limiting us. And in principle, we could spend up to our budget, but as any good bureaucrat knows, there's never any sense in spending less than your budget. So we are going to spend every dollar that we have, and here's how it would work out. It costs $10 per worker, and we're going to multiply that by the number of workers. It also costs $20 per unit of capital, and the number of capital units is K, so that's our total expense, and it should equal $3,200. In the terminology of Lagrange multipliers, that's our g of xy function. Also in the terminology of Lagrange multipliers, this is our function, and I guess I should have been more precise there. W and K would be our 2 variables of choice for this particular model, rather than x and y. So we have a function we'd like to optimize. I want to make this as large as possible. We have a constraint that has to be satisfied. And here's where you might see the idea of a change in constraints, or the idea that this is not some artificial constraint that has to be at $3,200. It's easy to imagine next week or next year that this might be a different budget value, but the same costs. And so we might want to explore the influence of changing the budget size on our optimal production. All right, so that being said, let's set up the Lagrange multiplier equations. We have 2 partial derivatives, w and w, and we take the function f and its partial derivative with respect to w. We'll bring the 3/4 down front, w to the -1/4, and k to the +1/4. That's going to equal lambda times, well, this whole left-hand side is g, the w derivative is just 10. Put a vertical bar there. We also have the k derivative of both functions, and similar logic. Let's go through here, differentiating with respect to k. The w stays the same as a multiplier, and then we get 1/4 k to the -3/4. That's going to equal lambda times the derivative with respect to k is 20. And last but not least, 10w plus 20k is going to equal 3,200. So those will be equations. We'll move to the next page. Having copied over the equations, we can number them in our usual style, 1, 2, and 3, and again remind ourselves of the goal, which is to solve for the optimal values of w and k. All right, if we do that, one strategy we can use is we have 2 things that are equal on the left-hand side of 1, and 2 things that are equal on the left-hand side and right-hand side of 2. One of the tricks that can sometimes be handy is to simply divide the entire left-hand side by the entire left-hand side here, and likewise the right-hand sides. That'll let us cancel out the lambdas without having to solve for them. It can be a nice shortcut. I'm going to keep everything the way it is, because we'll get more cancellations that way. So the first part is 1, w to the -1/4, k to the 1/4. Let's not put the equals yet. We're going to divide that through by the left-hand side of 2. And I'm going to put things, at least align the constants. And k to the negative 3/4. All of that is going to equal the right-hand side of 1 over the right-hand side of 2. And we are rich in cancellations. 6's, lambdas, the zeros, the quarters all cancel. So that's fantastic. And even better, that leaves us just with a constant of 3 on the left. And let's take the k's, it's a bit easier to see. K to the 1/4 divided by k to the negative 3/4. Remember, if we're dividing, we add the exponents if the bases are the same. So we actually get a k to the power 1 when we combine these two expressions. Likewise, we have w to the negative 1/4 minus another 3/4, that's w to the negative 1, or w to the 1 in the denominator. And on the right-hand side here, we have still the 1 and the 2, or a half left over. When we rearrange that, we can solve for w. Let's bring the w up. W is equal to 6k. So what that tells us is, for each at optimum, not any time we like, but any at optimum, the number of workers is equal to 6 times the number of units of capital. Okay, that's a good start on things. What we can do with that is combine it with equation 3, which we haven't used yet, our constraint, and hopefully solve for the optimal balance of, or number of workers and capital. So 10 workers, but each worker is 6 capital units. And we have 20 capital to start with. That has to add up to 3,200. And if we do this right, that's 60 and 20, that's 80k is 3,200, or k is equal to 40. To satisfy the optimal criteria here, we should spend enough money to buy 40 units of capital and put that back through equation 4. We get that the number of workers we should hire should be 6 times that, and that's 240. Fantastic. So that actually is our optimum production level. We won't go through the proof of why it's a maximum, not a minimum. Again, we can have some good sense that we want to stay away from w and k equals 0. This is a nice single maximum point we're going to find. And that is what we want to record here. The optimal, with one L, the optimal worker capital assignment is w equals 240 and k equals 20. Okay. Now we introduce something a little more about economic terms here. What we're going to look at is a term called the marginal productivity of labor and the marginal productivity of capital. Lots of fancy words, but if you think of marginal, it often is connected to derivatives. And in fact, that's actually how it works out. Marginal productivity of labor is dq dw, because workers are labor, and marginal productivity of capital is dq dk for capital. And the idea is, in the more explicit sense that economists use, we would say the value of the change in quantity if we set the number of workers up by 1, or increase the set of workers by 1, well, delta Q over delta W is approximately what we'd call the instantaneous rate of change, or that derivative. So another way to think of this is the rate of productivity per labor unit added, or the change in productivity, better way to say it. The change in productivity per labor unit added. So if that is a reasonable idea to ask, and it is one, I think, how much impact does the next worker have on the productivity of this company? One of the things we might ask is how we can look at this some more. So here's just putting that into bullet point form as derivatives. When we're at the optimum, we might see something interesting though. let's take a look. Check that at the optimum values of W and K, which we just found, the ratio of the marginal productivity of labor and the marginal productivity capital is the same as the ratio of the costs. Okay, whole bunch going on here. Let's get the first part. Ratio of the marginal productivity of labor to the marginal productivity of capital. That's the ratio of Q with respect to W and with Q with respect to capital. Okay. Well, we actually found that before. That was, we found these two ratios. It was 6 3/4 and W to the negative 1/4 and K to the 1/4. And we had 6 1/4, W to the 3/4, K to the 3/4. Those were our derivatives. We found those earlier. They were F sub Q F sub W and F sub K. And we were able to cancel a whole bunch of stuff, the 6s, the 4s, and we ended up with, let's stick with green, we ended up with 3 on top, K on the top, and W on the bottom. So that was just a ratio. Now, at the optimal value, we had K is equal to 40 and W is equal to 240. With that all combined, or that inserted, I guess, we would get that this ratio is 340 over 240, and that is 120 over 240, or better known as 1/2. So at the optimum, that's the ratio of the effect of one worker to the effect of one unit of capital on the productivity. Now, what was the cost ratio? The cost ratio is simply the cost of each unit. So here's a per unit effect on production and per unit of capital effect on production. What's that ratio? The cost ratio is even easier. It's the cost of W over the cost for every unit of capital. And we said, well, it costs $10 a worker and $20 for each unit of capital, which is 1/2. Okay. So these two numbers at the optimum are equal. Now we might be thinking, oh my goodness, what was going on here? Is this a coincidence? They both, 1/2 is a pretty common kind of number to come across. It's not a coincidence at all. In fact, this relationship that we just found, that at the optimum these two ratios are equal, is just a way of retelling the story of the gradients. Because if we look at what we started with, delta F is equal to lambda delta G, or grad G, sorry, then what we have here is our F sub X, F sub Y, F sub workers, and F sub capital as a vector equals lambda of G sub W and G sub K. Well, guess what all these ratios are? This is the marginal effect of workers on the productivity. So that's dQ dW, that's dQ dK, and these, cost per worker is exactly what GW is, cost of a unit of capital is exactly what cost per unit of capital is here, GK. When we look at that expression, what we can see is that the ratios of the first component to the second component have to be the same for both at the optimum, because they have to point in the same direction, and it turns out that that's exactly equivalent to having these ratios be the common thing, the same, this 1/2 here. So this discovery about economics is actually just a restatement of the Lagrange multiplier equations.